Again,
Right.
hold on, David. Let me give a little bit of a welcome, and then we'll get started. So again, good afternoon, and welcome to Lessons Learned Addressing Green Starvation During Saturated Conditions. My name is Stephanie Lewis. I will be your moderator today. Let me tell you a little bit more about David Florence before I hand it over to him. David is an assistant research engineer in the System Reliability Division at Texas A&M Institute. In his 10-year career, David has performed research for the Texas Department of Transportation, Federal Highway Administration, Crash Avoidance Partners, and a variety of other institutions. David has led research efforts to evaluate Q-responsive signal control in multimodal environments and impacts of partial autonomous vehicles on signalized corridors. Again, so David, his full bio is on the NICER website. So David, I'll hand it over to you. So take it away.
All right. Fantastic. Thank you, Stephanie. So today I'll be talking through a research project I did with NICER on addressing starvation of green during saturated conditions. This is a research project that came to being through one of the particular problem intersections and what it would mean to expand that to other intersections around the country. So we're talking through the results of this project. I put the report number here, NICER 4-9, so that y'all can find it later. Outline for today's presentation, I'm going to talk through exactly what we mean by starvation of green, talk through the proposed strategies and what we came up with and different ideas of how you might address something like this. I want to talk through the test bed, like I mentioned, that intersection in College Station that we selected as a test bed, deployment of our strategy and what we did to try and assist the transportation needs at this intersection, lessons learned, and talk through what we did and what we learned as we operated at this intersection for a few months, and some conclusions of that as we wrap up the presentation. So what is starvation of green? Essentially, it spans from closely spaced, oversaturated intersections. What it means is that some vehicles at one intersection just simply can't proceed despite receiving service because there's no storage upstream. In this case, I've generated this little graphic that shows the red vehicles experiencing starvation of green because even though they're being allotted service by the intersection they occupy, there is nowhere for them to go. So this is something that we see, like I said, closely spaced intersections where it's a problem. And so the research questions for this effort is how can we better ensure that we are displaying green phases of vehicles that can utilize it? There's nothing more frustration or more frustrating than receiving a green light, not being able to go anywhere. But nothing in our transportation network operates in a vacuum. So we wanted to know how are we impacting the neighboring intersections in the network. If we're sending these vehicles somewhere, what's it doing for the operations at those other intersections? And what strategies to improve performance, or what strategies actually work to improve performance at the problem intersections? So when it comes to mitigating starvation of green, there are a few different things we can do. One of which is withholding demand. This is referred to as metering often, where we're not going to allow the queue to continue to build. So in this scenario, we would not allow entering traffic to the storage link. We would give them a red indication because if you can't go anywhere, you might as well have the red light, right? So the idea is that we're not going to allot them service because there is nowhere for them to go and it wouldn't really matter. But of course, that can't be all that we do. We also want to increase service because there's clearly more demand on that subject link. So the idea is to allow the vehicles in that link to proceed, allow them more service. And then the real question is, do we do both? Do we do one? Do we do the other? And there was actually some previous research done on this subject in another NICER effort preceding this one, where we looked through this in simulation. And we ran some simulations to pursue this. This effort was about not only continuing that simulation, but deploying what we found, which was a Q flush strategy. So, and the other question is, well, what else? What if we retime the intersections? What if we look at different things? What if we do some combination? So the risks as we try to address this is, well, only withholding demand could still waste green time in the other direction. So you might be giving a green light to a direction that has storage upstream, but if there's nobody there, then that's also not really a win. Only clearing the queue could prevent service from conflicting movements. So that means that, in that previous image, there could be heavy traffic on the other movements that aren't experiencing starvation of green, but they still, they're experiencing cycle failures. So only clearing the queue could create where we're prioritizing one direction. We really need to be thinking about the whole network. Implementing both strategies could cause the most disruption. So if we do both, then we're metering and we're flushing, and this could lead to the intersection falling out of coordination if it is in coordination, and so on. And changing plans needs to account for, in this case, trains, which I'll review in a future slide. So looking at a test bed, we are at the Texas A&M University system. My office is near campus. So we selected and found an intersection in the College Station area. It's actually right next to Kyle Field, which is another big factor in this research, as we'll discuss. So I have the pin here showing where it is in the state of Texas. If we drill down, this is a little map, again, showing where Kyle Field is and the intersections of interest, which are just to the south of Kyle Field, with Wellborn Road and George Bush Drive. In the PM peak eastbound traffic, and again, this is in College Station, the whole city is at a little bit of a skew. So we call it eastbound. It's like Aggie East, which is the going from left to right on your screen, if you will. And even though it's a northeast street, we're calling it eastbound. And Wellborn, again, we'll refer to that as north and south. So eastbound traffic backs up in this area on George Bush and extends past Olson Boulevard, which is this road that comes to the south here. There's also the Aggie baseball Olson Field here. And so it will fill up this link entirely and extend way past it and even come past Penberthy and beyond. So southbound and eastbound movements are the peak directions here. So in the PM peak, the Aggies are trying to get away from campus, trying to go to their apartment to do their homework. So they're coming south or they're going east to try to get across the city. Traffic on George Bush and Olson will wait. Traffic on George Bush and Olson wait on green indications for the chance to move. Again, that's starvation to green, where they are just, they're sitting there with a green light. Vehicles on Olson often need to block the intersection to get any utilization at all. So what will happen is when vehicles on this link receive a green indication, there's nowhere for them to go, and driver frustration abounds, and they eventually will go on yellow or just go and wait in the middle of the intersection and block it entirely, because that's the only way that they're able to move. So the baseline operations, what are things like out there? Talking about Bush, Wellborn, the intersection that's immediately to the south of Kyle Field. We have a really pretty long cycle. This is the ring barrier diagram. 50 seconds for the turning movements, 55 seconds for the through movements on Wellborn. And then on Bush, we have 35 seconds for the turning movements and 55 seconds for the through movements. It's a pretty long cycle. And another thing of note is that there is an active rail line going along Wellborn. It runs in parallel to Wellborn across the city. This rail line receives upwards of 20, often closer to 30 trains a day. So this particular testbed does not run in coordination because of the frequent preemptions caused by rail, occasional preemptions caused by fire and emergency services. So if it runs, the city found that if it runs in coordination, it just remains in coordination. Excuse me, it just remains in transition for the entirety, which isn't really helping. Bush and Olson runs a shorter cycle length, and here there's a little bit of different duration for the turning movements on Wellborn, on George Bush. Phase 2 is that eastbound phase that we're talking about that experiences a lot of starvation to green. Phase 3 is coming out of the apartment complex just to the south of the intersection. This isn't a heavy movement, but it's still allotted a certain amount of time. It's really allotted as much time as it is to allow for the pedestrian movements because there's a heavy pedestrian traffic. Again, for Aggies entering campus, a lot of folks will cross here. Phase 4 is that southbound phase I was talking about, that vehicles will be waiting for the green indication. So what does it look like when these vehicles are experiencing starvation to green? We see these pretty long queues and folks sitting there, and it looks like my GIF is going to work over line. They're sitting there and getting frustrated and just waiting and wondering when are they going to get an opportunity to move. You can, in this image, you can actually see some vehicles at a skew here. Those are turning vehicles off of Olson that came and occupied the center of the intersection because that was the only way that they felt they were going to get any service. So what did we do in this project? We did a field deployment. We deployed the metering and flush strategy in April 2023. We also used INRIX and ITERIS signal performance metrics available to us. The ITERIS metrics are available to us through the city, and we used high resolution data collected by the signal controllers to evaluate how the field deployment was operating. We planned a revision, and we also did some addressing of issues that we'll talk about. And this project also involved a simulation effort where we used hardware in the loop to exercise some of the abilities of the controllers in the field. We calibrated the model, added some intersections, and we used simulation to analyze the deployment and upcoming strategies, kind of look through what is going to happen in that simulation environment before we put it in the real world. So what did the field deployment do? Well, we went and we visited these two intersections. This image is of a fellow researcher of mine and the signal tech at College Station teaching us how the configuration is for the radar sensor that we use to detect the cues. That radar, well, we'll talk about the Aggie football first. That's pretty important. So the original conditions, the city of College Station knew that this was a problem intersection. Like I mentioned earlier, this intersection tended to operate in free, and because that kept it from being in transition constantly. So despite heavy traffic along Wellborn, it did operate in free. They found that this signal timing minimized complaints. They were receiving lots of complaints at these intersections, but when they made this really long signal, it created, it helped relieve enough, I guess, that the complaints stopped. And, talking about Aggie football, this is being just south of the of Kyle Field. This signal timing allowed for easy operations for game day traffic. So they were able to convert and utilize game day strategies without needing to go and put a whole lot of effort into retiming the signals. So establishing the Q flush, well, we used previous efforts that we did in another nicer project, use AST3 signal controllers for simulation only. The challenge is that the city of College Station used Siemens N60s controllers. So that there's just enough discrepancy between these two traffic signal controllers that it wasn't really a fair assessment or even a useful ability to simulate how these are operating because the underlying structure and how you would code a Q flush strategy into these controllers were different. So we utilized hardware in the loop simulations and created timings for the M60s controllers. We used some spare controllers from the city. They were gracious enough to let us utilize these in our simulation environment and download the timing plans onto here. And then we could adjust that and put in the flush strategy. So previous research that we did used a preemption to establish essentially a high priority Q flush. That wasn't really an option here because all the preemptions were currently in use. Again, from the train, we did utilize some preemptions for a different flush strategy. We'll talk about that a little bit later. And then there was fire and emergency services in all four directions. So preemptions wasn't really an option, nor would it really be necessarily appropriate for this. So we used a priority routine and generated essentially a high-level priority routine that could operate much like a preemption without needing to use a preemption and allow other preemptions that are higher priority to go into effect. Previous research simplified our problem by removing the trains from the network. We didn't consider the trains. In this effort, we did simulate the trains, and we were able to incorporate preemption requests in the simulation environment and utilize that and allow what essentially would be simulated like a train. We didn't actually generate a train vehicle in the simulation, but we did allow it to block traffic for 5 or so minutes and then relieve it, which helped generate a realistic representation of the queuing. So we created tests to ensure that train preemptions are not disrupted, that this priority routine is not going to stop the controller from somehow entering its preemption. And so we incorporate that in the simulation. This is actually an image. You can see the train a little bit in the background here, peeking over those vehicles. You can see the train in effect. So now I can talk about the sensor that we used. To detect the queues, we utilize a sensor in the pit of the mast arm. This is actually pointed to service traffic on the other side of the roadway. This is pointed to service and detect vehicles on phase 6 going to the west. But it did have just enough range and just enough ability to actually detect vehicles below it. So it could point its radar and see vehicles in the area for the eastbound traffic. And so we use this to do a couple of things. We did establish the meter traffic scenario, and we put dynamic phase omits for phases 2, 3, 4, and 5. Essentially all the other movements, or all the movements that would be blocked or unable to move when the signal or when this link was full and when that area was occupied. We also used it to establish a flush at the downstream intersection using peer-to-peer. We did this by introducing some new phases. I'll talk about that a little bit in depth when I show the ring barrier diagram. And created a priority routine that calls these phases on the peer-to-peer communication between the two. So here's that ring barrier diagram talking through what it was like to add those phases. So you see we now have phase 9 and 10 in here. These are placed so that when they're complete, it will go and service the through movements and essentially continue this eastbound flush until it gaps out. These phases were generated with 35 seconds, which allowed enough time for the queue to discharge and the last vehicle in the queue underneath that radar to start moving. And then it would continue servicing again in phase 8 until it gaps out. So these phases were generated and they were only ever called by the peer-to-peer communications. There's no detector calling these phases. So as long as the link between these two intersections doesn't get filled, it would never service phase 9 and 10. This had allowed the ring barrier structure to operate continuously and to remain in this way, but it wouldn't call phase 9 and 10 until there's sufficient traffic or detection. What we did for Bush-Olson is we rearranged the ring barrier structure a little bit. What this allowed, we brought phase 5 and did a lead lag operation between these two. The point of that was to allow or to make it so that when phase 1 exits, it would go to phase 2. So this would allow when the flush is over, it would give more time to the through movement to the vehicles that are in the excessive queue on George Bush instead of on Olson. Again, this is oversaturated conditions. Both of these directions have lots and lots of vehicles on it, especially in the beginning of the fall semester before traffic has died down and leveled out. People have found their final routes that they prefer to take to and from campus. So this allows for when when the flush ends, when the phase 1, 5, 3, and 4 are no longer omitted, it would go to phase 2. So we deployed this on April 18th, 2023, after doing some bench testing and talking through the city about how exactly it would work. We utilized the simulation and some scripted scenarios for bench testing to confirm that it would be able to operate successfully. During the field deployment, there's always something. We adjusted the radar sensor to help us better detect the cues. This was adjusting the parameters. That radar sensor that I showed in the earlier slide was configured to find stopped traffic. It was able to detect the speeds of vehicles, and so it should have only actuated the Q flush if a vehicle was stopped, which we define as a speed less than 5 miles per hour, and if it was underneath the mast arm. So in that region, that represents the Q is full. So we tried different methods for establishing metering. We had some hiccups on the deployment, and we did eventually find a way to get it to work and operate it. So results and discussion, I'm going to show some of the results that we had from the field data and what we did in the simulation. I have some specs on the simulation here. Essentially, 1 hour simulation with a warm-up period, and we did 3 different scenarios. The baseline, which was what was out there before we deployed, priority flush, which is the strategy I just described, where we use the priority routine to do a Q flush with metering. We also did a retiming scenario because we thought that the signal links were very long, or the cycle links were very long. And so we did some simulation and look at what it would be like if we shortened those cycle lengths. Even though that might reduce capacity overall, it's already saturated, and the idea was to keep vehicles moving. We did 10 simulation runs for each scenario. I'm going to talk through first the field analysis. We used INRIX. INRIX was gracious enough to allow us access to their data and utilize that. We used their signal analytics tool, which they offered to us to compare probe vehicle data before and after deployment. So this is immediately before and after, comparing the 4 weeks previous to deployment to the operations after deploying the strategy. And we also did delay in travel time on road segments between 2023 and 2022, looking at essentially what it was like across the 2 different years. So talking about the cumulative distribution functions for signal analytics, these graphs show essentially a comparison between what currently is what the operations were for a time range to the previous 4 weeks. This is looking at, I believe, the PM peak period. And we have this solid line representing what's happening currently and the dashed line representing the 4-week average cumulative distribution. And then they would add in these colors to help you identify, is it going down? Is it going up? And how do these compare? What we found for the eastbound approach at George Bush and Olson is that the delay experienced by vehicles went down with some significance, 40% reduction in delay and a 33% reduction in travel time. We also noticed that there's a reduced variance between the two, that the vehicles that have the longest delay are lower than in the after period than in the before. For the southbound approach, again, like I said, we don't do anything in a vacuum. So the southbound vehicles, we looked at what was happening to the vehicles coming off of Olson. Their story was a little bit more mixed. The variance didn't necessarily change much. We did have some that made it through there faster and others that made it through there slower. We did reduce the maximum delay per the readings, and that was kind of expected. This wasn't necessarily to serve them. What was hopeful about this is it didn't really get worse for them, which we'll talk through. Like I said, we compared 2022 data to 2023. We grouped Mondays and Wednesdays together, and we did Tuesdays and Thursdays separate. This is because of the class schedule being next to a college campus and the way that they structure their classes, Mondays and Wednesdays are a better grouping than trying to group the whole week together. This is for the PM peak period, and the dashed lines are the after. So this is with the deployment. We saw that the travel times were overall across the period lower in the second year. Again, we assumed for the sake of this that the traffic was about constant. It isn't necessarily true. If anything, 2023 would have more traffic than 2022. Looking at Tuesday and Thursday, this also we saw in the after period that the travel times were lower. So that was hopeful. Simulation, and like I talked about, we did these simulations, 1 hour simulations. This is an image of the setup that we had where we connected the traffic signal controllers. We put two signalized intersections using hardware in the loop. We did have other intersections in the model. We did 6 intersections around this little test bed, including the test bed. And George Bush and Olson and George Bush and Wellborn, the 2 subject intersections I've been talking about, were using hardware in the loop simulation. So we set it up where 2 signal controllers had the base timings, 2 had the retimings, then we'd switch it up, download a new timing plan when we looked at doing other versions. And so this considered trains, buses, and pedestrians. We had pedestrian recalls at Bush and Olson, or I think actually at both intersections, because there's essentially constant pedestrians during these PM peak periods. Simulation results in the baseline, travel time would increase and increase and increase throughout the simulation period. And when we put in the other strategies, priority, queue flush, again, what we deployed, that showed lower, and these are similar travel times, a little bit higher than what we measured in the field, but similar nonetheless. Retiming, it looks pretty good for that eastbound. And we also even looked at a double cycle where Olson operated half the cycle length of George Bush, and that did pretty okay. Looking at southbound, this is vehicles coming along Wellborn. Not necessarily our target, but again, we're looking to make sure that we're not making things worse for them or significantly worse for them. This is vehicles that went from essentially a 1.5 mile stretch through the facility. And it says this essentially told us, one, that what we deployed could have made things a little bit worse for southbound traffic. Not a big surprise. It was nice to see that it wasn't making it much worse. And this indicated that the retimings and doing a double cycle would help keep that southbound traffic moving and perhaps improve on what the current operations were. We looked at queue links. Like I said, we had 6 intersections total in the simulation. So the 2 intersections that we've been talking about for the most part are these 2 on the left, and these represent intersections surrounding our test bed. Looking at the queue links here, we saw a 611 vehicle queue at George Bush and Olson's, averaging all the movements together, trying to be holistic but broad. And we could see a reduction in the priority or in the queues when we look at the different strategies. Wellborn and George Bush, our major intersection, also oversaturated. The queue links were relatively stable when we looked at the big picture, but when we drilled down and looked at queue links for different movements, the picture wasn't as rosy. When we looked at westbound through at Wellborn and George Bush, we saw the queues triple for the westbound direction, which wasn't really a good sign if we were thinking about deploying this. We also saw southbound throughs increase with the retiming. Again, that wasn't as concerning as to say the queues tripling. We looked at other movements for the left turns, and this also showed a significant, it increased by 10-fold for the westbound left turn, which we knew was a heavy left turn movement. Again, every direction here is saturated. And northbound left turn, this also went up 4-fold for the vehicles trying to turn from Wellborn George Bush towards Olson. Ultimately, that led to us deciding not to deploy the retiming strategies or the double cycle strategies, because we had an understanding from the simulations that it wouldn't necessarily help some of the key movements that we knew folks would be worried about. If we do something that increases a turning movement's queue 10-fold, we knew that would pan over well. So lessons learned, I'm going to talk through a few of the issues that we encountered during the deployment. These are things that we had complaints with citizens. There's a portal that citizens can submit complaints to the city of College Station. They, of course, knew that we were doing this deployment, and so we'd have a conversation with them anytime that a complaint about these two intersections in our test bed came up. So there was a lot of back and forth, or not a lot of back and forth, but there was back and forth between what they had and what they received from citizens and what we could do to help and address that. So I'm going to talk through the three different issues that came up. One, we actually identified with the simulation was a redundant queue flushing. This was a queue flush that happened after the train. We also got some complaints. This was one that we found complaints of about a no service scenario on Olson Boulevard. And we also identified some unreasonable queue flushes. So let's talk about redundant queue flushing first. This was something that we observed in simulation. I actually was watching the simulations and the animation in there during data collection from the simulation tool. And I noticed that after a train preempt ended, the signal would go immediately into a queue flush, which isn't really what we wanted. We didn't, what would happen is there was some legacy control in the signal controller where after a train comes through this intersection, the intersection would try to flush the queue. It had actually a preemption that would flush the queue depending on how long the train preemption lasted. So this was meant to relieve traffic, something that was installed separate from this research effort, and meant to, again, ease congestion for that eastbound movement. But what we found is the train, this preemption flush would happen, and then immediately afterward, we'd have a priority flush from our efforts. With the new efforts, the second flush would occur only a few seconds after the end of what was already in the controller. We looked at the signal performance metrics and reviewed what was going on in this timeline. It shows these orange moments where the intersection at George Bush and Wellborn was in preemption. And we see the preemption requests represented by these orange markers and the orange little bar here you can see. And so this first preemption was the train coming through the network, and then the second one was that flush that I talked about. And we see in this PM peak period 4 different trains and 4 different flushes, depending on how long they were. The green checks is our system. This is when the system says, hey, there's vehicles stored in the link and they need service and they have nowhere to go. And so what we see these checks that happen during the train. You see them happening during the orange here. And we found that even if the first queue flush cleared these vehicles, the signal controller would remember the request, the priority request, and service it immediately after the preemptions ended. So what we did to address this is working with Iteris folks, we created a new special function, a new unit phase bank, and essentially came up with a way to say when a train preempt is occurring, we would cancel the peer-to-peer communications between the two. And so this step accomplished logic. We did some bench testing to confirm that it would stop these redundant flushes, confirmed that, and developed instructions on how to deploy this in the field so that the deployment could go smoothly. And we deployed these changes on September 15th of 2023. And again, pulled up our performance metrics, checked it, and saw that there were no longer check-ins. We didn't see the request for the priority flush during train preempts anymore. So that was a successful way to address these problems. The second issue that arose during deployment was in what I'm calling a no service scenario for Olson. We got a few complaints. The city received 3 complaints overall, each complaining about a drastic amount of time between green indications. The first complaint was about somebody coming out of the apartment complex. They didn't know it was phase 3, but they said that they had a 10-minute wait. Which at first we thought that's pretty extreme. You must be exaggerating. And then we looked at the signal performance metrics, confirmed that they had a 617-second wait time between phases, between service for phase 3. So we were humbled by that and looked through and tried to figure out what was going on here. We came up with one method. The first thing that we did is we said, well, what if we rearrange phase 3, bring it after phase 4, and remove the omit from it, essentially allow vehicles coming out of the apartment complex to get some green time. The reason it was important to move it after phase 4 was, again, when the omits lift, when we stopped metering, we wanted to make sure that phase 2 came up before phase 4. So rearranging that ring barrier structure ensured that we'd be giving the additional storage to eastbound traffic as opposed to southbound traffic. We deployed that and thought things were dandy. And then on October 12th and October 25th, we received additional complaints, this time for phase 4, also saying 10-minute wait times. We looked into it and found in the October 25th scenario that travelers were facing this no service, and the city actually recorded some video and confirmed that vehicles weren't receiving any service. In the October 12th scenario, we also saw indications in the signal timing that vehicles weren't getting service. We looked for a different way to make more conditional metering, but did not find functions available in the traffic signal controller. So we ultimately wound up removing the metering strategy because it wasn't functioning, and we certainly didn't want to create a no service scenario for Olson Boulevard where vehicles are waiting 10 minutes between receiving green lights, because essentially the takeaway was it's better to get a green light and not be able to go anywhere than to sit there for 10 whole minutes and not ever receive a green light. We got unreasonable priority flushes. This is, again, something that we saw in simulation and saw during multiple field visits. We had a constraint for the priority routine where it wasn't supposed to happen at more frequently than 360 seconds. Essentially 6 minutes between flushes. Again, we don't want to disrupt ambient traffic by constantly prioritizing the eastbound movement. However, we found that the signal controller would request 150 check-ins during a 4-hour peak period. It's like once every 96 seconds. It didn't really make sense. In multiple field visits, we saw check-ins on these controllers, requests for priority flushes from traffic in motion coming out of Olson, essentially vehicles turning with a close headway, and it would generate a check-in. Ultimately, and unfortunately, this wound up unresolved. We didn't find a way to address this. We didn't really fully understand during the life of the project why this was happening. And so what we did find is that from the data, that we did improve operations, and we did find, and the city ultimately kept this in. So it's still operating like this, and sadly, we still don't understand why it's doing some of these things. So I'm going to review some of the key findings before we jump into some questions and answers. So 6 key findings that we had out of this project. Both preempt and priority routines can provide queue flushing operations. We were able to generate strategies in both cases. Generating a metering and flush strategy can be accomplished with peer-to-peer communications. All of this was driven by peer-to-peer. So at one intersection, essentially was doing a peer-to-peer, but talking to itself. And we also, of course, had peer-to-peer between the 2 intersections. Queue flushing can be effectively accomplished with special phases added to each ring. Like I mentioned, we added phase 9 and 10. These were only called by the peer-to-peer, and it operated very well. We found that our VISM model helped us detect a problem in the field. We saw something strange happening in simulation, double checked it, and then went out in the field and confirmed that, oh yeah, that is actually happening. So big takeaway there was always review your animation for your simulation. You never know what you're going to find. Priority check-ins during a preemption were remembered by the controller. We talked about that, about how we saw these priority check-ins, and And once the preempt was ended, the controller just proceeded to serve as priority check-in, despite maybe a timing out or the condition no longer being true. So that's something to keep in mind as you're using priority routines for these M60 controllers. And timers for the limit of queue flushings, allowing the 6-minute limit I talked about weren't effective. Somehow it didn't use the 6-minute timer. We saw flushes happening more frequently than once every 6 minutes. We saw check-ins happening more frequently than that. And ultimately, it was unclear why any of this was happening. So there's always a need for more research. With that, I think we have some time for questions and answers. Stephanie?
Great. Thank you so much, David, for all of the wonderful information about the research. I will just quickly remind everybody, if you would like to ask David a question, you do have access to both the Q&A and chat box, which is located at the top of your screen. Sometimes that Q&A box doesn't work for some individuals, but you do have that chat window. So it looks like we had a number of questions already submitted. The first question says, why didn't you retime the corridor for the increased capacity?
Yeah. So like I mentioned in our simulation, we did consider retiming and using a shorter cycle length to try to keep traffic moving. That proved, the data showed that that wasn't necessarily effective, but why not give more time, right? So essentially when it's oversaturated, you don't necessarily want long cycle lengths. Long cycle lengths lead to even more just sitting and waiting for green time, and it leads to your queues being longer. It boils down to needing a different strategy for oversaturated conditions versus undersaturated conditions. If we believed we could get it undersaturated again somehow, increasing the cycle length could help, but since it's oversaturated and we don't know where that mark is to get from one operating condition to the other, the strategy needed to be to address oversaturation and keep traffic moving and manage the queues as opposed to servicing everybody.
Great, thank you. This next question says, what was the city of College Station's perception of the deployed system? And in the end, did they keep the final operations?
Yeah, the city liked it. We all were concerned by some of the complaints that came in. We found that we were able to address some and not others. But overall, the city found that it was helpful. They were able to maintain game day operations with this strategy in place. There was a lot of discussion on how do we use this new system to address every day, but also maintain what we needed to do for game day. So we found that this was a good medium. The city liked it, and talking to them as the project was coming to a close, they said, we're going to keep it in place because it does seem to be making things better.
Great. What were the key limitations of deployment, and how would you address them?
Yeah, so one of the key limitations, I think we got a lot of those false check-ins from the turning movements because our sensor that drove the tool wasn't designed for detecting queues. It was a radar sensor, and radar sensors historically don't do well finding stopped traffic. It was actually impressive how well it did finding stopped traffic, to be completely frank. So we found that maybe using a different sensor, if I were to do it all over again, and if I were to have the ability to select a sensor, I would go for something maybe more in ground sensing, use something like a magnetometer puck, or even use video to find the stopped traffic. Video detection is actually proven to be pretty good at finding stopped traffic. So there would be some different methods. And probably first thing I'd do is look at a different way to drive our flushing so that maybe we don't have the trouble finding stopped traffic.
So this question focuses around the scalability of this particular research project. So how can this research apply to other corridors or facilities, maybe even around Texas or around other states?
Yeah, thank you for asking that. This does at the surface look like something that is specific to these two intersections, but really there are lots of intersections around the nation that have similar struggles of being near a rail line and having this. I forgot to mention earlier, we have buses going through and across this rail line regularly, which limits our saturation flow rate. There's lots of different things going on here. And at the bottom line, if when we look at this, it is oversaturated conditions with the inability to operate in coordination. So we find if there's a use case later or even in a different place where you are running in free, but you already have a long cycle length and are struggling to get service and have one direction that you need to really reduce the queues on, this is one thing that could be applied. You could use something like a flushing strategy, build some limit, and say, we want to allow more service to this or these conditions, to this direction and this movement if these conditions are met.
Okay, David, thank you so much for taking the time again for this presentation, as well as for answering all of the questions. It doesn't look like we have any additional questions in the queue. The evaluation is on your screen. Simply click on the link or scan that code with that QR code with your phone and it'll open. It doesn't look like at this particular moment any new and upcoming webcasts will be available on the NYSER website at nyser.usf.edu. So again, on behalf of the National Institute for Congestion Reduction, thank you so much for attending today's webinar, and we'll see you all real soon. Bye, everybody. Bye, David. Thank you.
Yeah, it's my pleasure. Thank you. Bye-bye.